Our next speaker is David Minh.
All right, so I was invited to give a 10-year retrospective, and then I declined because I thought it seemed really intimidating. But then I saw people do it, and I thought, oh, that's kind of fun. It could be kind of fun. So I decided to start my talk that way, talking about, well, first of all, just about me. Although some people that I've met may think I'm a grad student or postdoc, I'm actually a tenured faculty member, and I've been working in these for a while. And I've never been an organizer, but you can call me I don't know if this uses slang anymore, an OG participant of this meeting, and I like to dabble with ideas. So I want to thank the organizers, but I want not to just thank the organizers of this conference, but for all the organizers of this workshop ever. And well, I always learn a lot coming here, and that's just one part of it, but I think this workshop has been more than just my own personal learning. I think it's catalyzed the transition of free energy methods from like academic curiosity to something that is being used, even by medicinal chemists. So I looked back at my own talk titles, but I also looked back at the 2014 meeting. And in that 2014 meeting, there were a series of questions that were being posed. And I just wanted to give my own opinions to the answers to these questions real quick. So back in 2014, there was a moderated lunchtime discussion. What is the state of free energy methods in drug design? And well, now 2023, it's useful for lead opt. And there's other emerging applications, and even synthetic medicinal chemists are starting to use it. So that's exciting. That's what we've been looking for. What about in 2014? What kind of pipelines and tools? We didn't really have a lot back then, but well, we have a lot now. I mean, they could be worked on and improved, but we've gone a long way, and I wanted to just point that out. It didn't have to be this way, but it's happened, but a lot of people in this room have helped it happen, and I've only done not really much of it. Okay, so what about calculation standards, best practices, and health do we need to assess simulations? And yeah, that's become a lot more standardized. I see people report the same correlation metrics across the different slides, which wasn't something that happened 10 years ago. People are using MBAR, even in FEP+, I understand. And at least people will know when something is off. And sometimes they'll look into it and sometimes they won't, because you can do a lot of these calculations now. So that's a good progress, let's say. And then what kind of experimental validation do we need? Because people are just picking out their own data sets and saying, hey, this looks good on this data set, so this is a good method. Well, we have these now. We have the JAX 15 set. We have this update that I heard about yesterday, and then the controversially named Merck set. Well, there's also been sample and D3R and other efforts out there. So yeah, we've come a long way, and again, there's limitations to these sets. Maybe they're too hard in some cases, but I thought it'd be good to recognize that we're not the same place we were, and it didn't have to be that way. What sort of force fields and parameterizations are needed for effective drug design? So the question back then is, can this actually be useful? And I think a lot of people say that it has become useful. So yeah, okay. We have these fixed charge force fields that we beat to death, and they're these expansions that are highly truncated and not these long distance correlations like John was mentioning yesterday. But it seems to be pretty good, or good enough for many systems to at least guide the discovery in some sense, and you can get better, as Jay was talking about yesterday with a polarizable force field. And um, there's machine learning force fields coming out that could do even better. So I'm optimistic that it could be, we're at a point where, well, that we are at a point where we can be helpful for drug design, which we were not in 2014. Or we weren't convinced that we were. So what happens now? What are the next steps forward? Good question. I don't really have an answer fully. I have the same questions. I ask another one to that as where should the academics like myself, where should we focus our effort? And I've sort of got some answers over lunch, but I think that's something we all can discuss and figure out how we all fit into this community. Okay, so that's a brief retrospective of the field from my perspective. And I want to talk about the next section, some excerpts from my own presentations over the last 10 plus years. And also, this is serving an introduction to what I'll talk about today. So yeah, I've presented a number of times, and I've worked on some other areas that are relevant that I'm not going to talk about today and didn't talk about before. But if you are curious about it, you can see my website or whatever, or the internets. So yeah, I started doing something that was kind of off the wall, but maybe some people are doing non-equilibrium stuff now. And then I started digging into this approach to do binding free energy calculations to rigid receptors, and then combining information from multiple rigid receptors. That's the implicit ligand theory, which I pushed for a while and then paused a little bit. If you look at my 2021 talk, it's recorded, then you can see pretty much the state of the art. So I'm just going to give a quick excerpt from these. So I don't come from, well, I guess this is not methane to ethanol. It's just a double well. So I guess it's even simpler. But this is where I started thinking about free energy, or one of the early things I was thinking about free energies, in that if you do a non-equilibrium pooling process, sometimes the distribution that you observe looks like a distribution in equilibrium for the protocol or earlier stage in the protocol. So I noticed that, and I talked about this in 2010 briefly. That's why I got invited back, which is, I said, well, you can do importance sampling in path space. And you can say, if you generate trajectories with one protocol, you can say that they came from another one. And you can evaluate this ratio of probabilities for observing the paths and do work in the new protocol and get a sample average. And then this seems to get more precise free energies, although it's not the exact free energies that you're looking for. At least it's more precise. It's converged better. And you actually have to pull it past your target stage to reach the free energy you're actually looking for. So yeah, this seemed to work. And I actually presented this with Chris Jarzynski's group, and he was, one of his students is like, hey, you can do this with Feynman-Kac integrals. And that actually was better than what I was originally throwing out with importance sampling. So the blue line is Jarzynski's equality. Red line is with the importance sampling formalism, and the magenta is with the Feynman-Kac formalism. So I don't think that got a lot of traction, although it might someday, who knows. But I was dabbling, because I was able to dabble into these path probabilities, then when I heard about what became known as NCMC, I was able to contribute to the derivation, and that's how I became an author, and that's how I could propose a name in the author order for this mouthful. So whenever you hear people complain about GC, NC, MC being a mouthful, you can thank me for it in part. At the end of 21, I had a new postdoc, and I had a new idea, which I briefly mentioned, this implicit ligand theory idea. And that's why I talked about this in this workshop previously. Illinois Tech is where I'm a faculty member, and this is in the south side of Chicago. In the middle of the slide is where my office is. So what is this implicit ligand theory idea? I've talked about a few times, but maybe some of you haven't heard or forgotten. Basically, it's a way to get rigorous binding-free energies and use multiple rigid conformations of receptor. And the binding free energy is an exponential average of the binding free energies to the rigid receptor. That's the binding PMF, which is an exponential average of the interaction energy or of the potential energy, and it's related to the potential energy. Okay, so then that's the theory, but it's kind of hard to do the actual calculations. So I wrote a code to do this. And then I started attacking some of these problems that we're talking about in absolute binding free energy calculations these days, which is why I'm going to continue talking about it with a flexible system. But I started talking about a rigid system, a rigid receptor, and that became my playground for working out how to get an alchemical schedule. I wasn't going to talk a lot about the schedule idea, but we worked on this idea, or I worked on this idea of thermodynamic length that with John Cadera at some point we worked on this. And basically, the ideal protocol has equal spacing and thermodynamic length. And I suggested that you could sort of trailblaze. You can start doing this by doing a simulation in one state, getting a thermodynamic length estimate to the next state, and then sort of having equal steps in thermodynamic length as you go along. And this was a form of sequential Monte Carlo that Jonathan Essex alluded to, but I didn't call it that back then. So yeah, that's what the different different ensembles look like as you go from like unbound, anywhere can be state to a bound state. So then I thought, well, let's try this thermodynamic length idea and optimize lambda schedules for many different types of things and try it out and see how much it improves the efficiency, because we want to have a good optimal schedule, right? This was surprising, but true. It actually didn't matter after a while. That is, if you increase the number of windows, the total sample size is what dictates your variance in your free energy, not the actual, there's no maximum, basically. That's what we found out empirically, and then we tried to figure out the theory behind it. It's all in this paper in JCTC, 2016. So if you have too few windows, K equals 18 for heating of decaalanine, you get this behavior, you increase sampling, you just get stuck, or sometimes you just get trapped. A decaalanine pooling, same thing. There's two numbers of windows, 8 and 16, where you get trapped, but other things, if there's no bottlenecks, you get a steady decrease in the standard deviation across multiple replicates. This is not a estimated variance. It's not based on like asymptotic variance. It's just doing the calculation many times, 100 times each, actually. Because these are small systems, we could do it 100 times each. And then host-guest extraction, also same thing. You just can't, there's situations where you get bottlenecks and replica exchange, but if you don't, then you actually get good convergence. So all this clever stuff that I was so proud of with thermodynamic length turned out to be, we can just insert more states, and it's okay. So somewhat disappointing from an intellectual point of view, but also I think useful and maybe underappreciated. I think people are not recognizing this yet. Anyway, so then when I wanted to do this absolute binding free energy calculation to a rigid receptor, I said, okay, we'll just do a lot of states and we'll adapt. Well, okay, we'll do this adapting thing for the initial protocol of binding or unbinding, and then we'll just add more states in whenever you see a gap. So we get this large number of like hundreds of states between, well, this is for solvation, this is for binding, and these are like 85 different systems in the Aztecs diverse set. And these are the replica exchange probabilities between neighbors. So there's a line for the acceptance probability between the lambda, well, alpha or temperature values for the states. So most of the time, the exchange rates, well, with solvation and raising the temperature, that's almost 1. Because we can. We don't need to make it low. We don't need to make it 10, 20. I mean, I think people are happy with 20, but actually 20 is not good enough. I guess I didn't say that point. This magic number, where is it good enough that you have enough states? And it's not a bottleneck. It seems to be 35%. So the theory is described in the paper that at this asymptotic limit, you have enough states. You don't need to add more. But where is that? That's something we had to figure out empirically. It seemed to be 35%. There could be some connections with phase overlap measures, but I haven't figured that out yet. Anyways, okay, so what's going on here with the grid scaling in? Most of the time, between 80 and 100% exchange rate acceptance. And then there's suddenly this big drop. Well, that's because in the initial trailblazing, 5 minutes, huh? Okay. The initial trailblazing, it was high acceptance rates. But then there was a conformational change a little bit later in the simulation, and we needed more states to get a transition to that conformational change. Okay, so these calculations did converge, at least in the parts that were not bookends. The way I did this thermodynamic cycle is simulations in these states with replica exchange, and then there's these bookends with free energy perturbation, essentially. And those ones are higher variance, but these, for almost all systems, at least, less than 2 kT. This is the number, the convergence as a function of the simulation time. So as you go to a larger simulation time, then you get more and more of the systems are converging. For this free energy to rigid receptor, absolute binding free energy to rigid receptor. And then I applied this to comparing to docking, and seemed to get better. But at this point, he wasn't sure exactly what made it bad. So David Mobley suggested, hey, why don't you do one system really well instead of just like trying this on a bunch of systems and maybe not so well. So we did this for T4 lysozyme, and that seemed, well, after some time with receptor conformational sampling, we were able to do this to reproduce an alchemical calculation with a flexible receptor. We also tried doing this, applying this to Markov models. Haven't published it yet, but it seemed to be promising. And we also looked into like whether something's an agonist or an antagonist, and it seemed to distinguish that pretty well for the estrogen receptor. So those are the things I presented before. So I don't have a lot of time, but I want to talk about what we did now. This is mostly done actually by an undergrad and a grad student who did some development of the Yank a little bit to do some state insertion. And yeah, we know this is a big challenge still. And well, what we did, we prepared systems with all these different docking poses. We did this trailblazing, and then we did an initial replica exchange and inserted states. And then we replaced these replicas with the prepared systems with the different docking poses. And then we just sort of let those states battle it out in another replica exchange. And then we analyzed what is the population of the coupled state in this pose. I guess I'll go quickly because I don't have a lot of time. But yeah, we used John Kadera's lab's Yank code. We just wrapped it a little bit more. And so we first get the lambda schedule, or initial lambda schedule, initial replica exchange. And then we replace everything with the new poses, and then see how it swaps. And then we tried this on the mu opioid receptor, which has a bunch of biased and unbiased agonists. The biased agonists will go towards the G protein pathway or the beta-arrestin pathway. I won't go into detail about that. But docking, we never get the top pose anywhere near the native pose. And we don't always get convergence yet. We only did this, so this is like a week old. But yes, some systems we get pretty consistent results across triplicates. Sometimes we get a big difference. sometimes we get positive free energies. So this is not working as nicely as this rigid receptor stuff. So yeah, things could be happening with the protein lesson. um, but okay, this is maybe hard to see, but docking, basically, there's a bunch of poses that have almost the same free energy. Now, this is autodock vena, high exhaustiveness. And then, but then if we do this filtering thing, there's many situations where we only, or pretty much we identify, we throw out those poses that have low energy according to docking, but they just don't exist anymore in this fully coupled state in the alchemical replica exchange. And here's one of these systems, and comparing to the cryo-EM structure. So it does, in this case, it only keeps the native poses, whereas the docking kind of throws them away, or assumes that or it throws away these poses which have high RMSD and have a similar docking score. And in this state, only one of the replicates worked. So maybe if we ran many replicates, well, at least we could tell if it doesn't work if they have a really different free energy. But in this case, that one replicate did get a low RMSD to the native and low energy. And then for low fentanyl, there's actually has been some debate about how it fits into the mu opioid receptor pocket. And you can see that, well, there is a low RMSD pose, but then you can also say that it's not completely clear what the pose should be, because you just see this sort of electronic blob, and you can rotate the ligand to fit in the other way. So we're still looking into this, but there is a possibility that the cryo-EM structure is not exactly correct. Here's another ligand that, yeah, we throw away bad poses. So I'd say that we don't have full definite conclusions, but I would say that high replica exchange rates are necessary but not sufficient for convergence, because we don't always see convergence yet, but maybe we will if we run it a bit longer. And in many cases, it appears that doing this outperforms docking and MMGBSA. Oh, I didn't talk about MMGBSA in detail, but that's the interaction energies on those plots. So any questions? Okay.
David, so I want to thank you again for pioneering the non-equilibrium switching free energy calculations. A lot of us are using them in anger right now in discovery programs. So where do you think things are going to go in the future with non-equilibrium and equilibrium methods? Do you foresee some sophisticated combination of sequential methods, or what's next for non-equilibrium, since you appear to have a 10-year head start on everyone else?